Okay, so from some of the things that we went over last class, for a polynomial function, which is what this is, first thing we want to talk about is that end behavior. The end behavior is determined by two things. One, the coefficient on the variable with the largest power. That's this right here. That's actually a 1. That's positive. And then the highest power, which is a 4. That's an even power. Even power means both ends either go up or both ends go down. Positive coefficient means both ends go up to positive infinity. I don't need the positive in there, so I'm going to take it out because it looks confusing. It looks like a T. So that's our end behavior. Next, we need to worry about what our roots are. We know that there's going to be 4 roots because there's a power of 4. It's a 4th degree equation. The highest power is 4. To figure out how many positive and how many negative roots, we can use Descartes' rule of signs. So as we go through this, right now as it is for the positive roots, this coefficient is positive, that one's negative, negative, positive, negative. So as we look at that, that's one change, went from positive to negative, still negative, negative to positive, that's a second change, positive back to negative, that's a third change. So positive roots, there's either 3 or remember it can decrease by an even number. So there's either 3 or 1, but there is at least one positive real root. For negative roots, we need to have f of negative x. So if I put negative x in for x to the 4th, and negative x in for the x to the 3rd, negative x into the x squared, and so on. Well, negative x to the 4th, well, to the power of 4, it doesn't matter. It's still a positive x. So that's x to the 4th. X to the negative x to the 3rd, though, is a negative x to the 3rd. So negative 2 times negative x is a positive 2 x to the 3rd. Negative x squared is just a positive x squared. So negative 4 times positive x is negative 4x squared. 26 times negative x is a negative 26x, and then, of course, the negative 21. So here we are positive, positive, negative, negative, negative. So if we look at changes, that's still positive. There we went from positive to negative. That's one change. Negative to negative, negative to negative. That's 1. There will be one negative real root. So we know that there's one negative root, and we know there's 1 or 3 positive real roots. If there's only one positive root, remember we said there has to be 4 total, that would mean the other 2 are complex roots. So back to our original function here. F of x equals x to the 4th minus 2x to the 3rd minus 4x squared plus 26x minus 21. we use our rational root theorem to find possible roots. Remember, we take Q is off of the coefficient of our largest power of the variable. That coefficient on the x to the fourth is a 1. The only factors of that, the only possible values of Q are 1 or -1. P is our constant term. So it comes off of that -21. So the factors of that are 1, 3, 7, 21, or -1, -3, -7, and -21. So all the combinations here is going to be all these numbers divided by either 1 or -1. That gives us 1, 3, 7, 21, -1, -3, -7, -21. Those are the 8 possible values for our roots. So how do we evaluate to see if there are roots? Well, that's where we use our remainder theorem. Remember where we said the remainder theorem is if we take f of x divided by x minus c, the remainder of that division will be f of c. So if consequence of that is if f of c equals 0, then x minus c is a factor. And remember, a factor is where we get our roots. So if x minus c is a factor, that means that c is a root. I'll scroll that up in case that's blocked by the corner of the screen. So let's come back up here. So to test to see if any of these values are roots, we're going to substitute that value in for x and see if it gives us a value of 0. So let's find f of 1. That's our first one we're going to try. That's 1 to the fourth minus 2 times 1 to the third minus 4 times 1 squared plus 26 times 1 minus 21. Now I should be doing proper order of operations here, but to make life go quicker, I'm going to take some shortcuts. 1 to the fourth is 1. 1 to the third is 1 times 2 is just 2. 1 squared is 1 times 4 is just 4. 26 times 1 is 26, and then minus 21. 1 minus 2 is -1, minus 4 is -5, plus 26 is 21, minus 21 is 0. So I get 1 is a factor. Or sorry, 1 is not a factor. I should say 1 is a root. So that means x minus 1 is a factor. So we've got one factor. If we want to do -1, let's try that. So that's going to be -1 to the fourth, minus 2 times -1 to the third, minus 4 times -1 squared, plus 26 times -1 minus 21. Well, negative 1 to the fourth is 1. Negative 1 to the third is negative 1 times negative 2 is a positive 2. Negative 1 squared is 1 times negative 4 is negative 4. 26 times negative 1 is negative 26. And then the minus 21. Well, 1 plus 2 is 3, minus 4 is negative 1, minus 26 is negative 27, minus 21 is a negative 48. 1 is definitely not a root. So let's try 3. Now, one significance here, if 3 is a root, that is a second positive root. If we have 2, we have to have 3. Remember, it's either 3 or 1. So f of 3, this is going to be 3 to the fourth power minus 2 times 3 to the third minus 4 times 3 squared plus 26 times 3 minus 21. 3 to the fourth power is 81. 3 to the third is 27 times negative 2 is negative 54. 3 squared is 9 times negative 4 is negative 36. 26 times 3 is a positive 78 minus 21. So let's see what we get here. 81 minus 54 is 27. Minus 36 is a negative 9. Plus 78 is 69. Minus 21 is 48. That's not a factor. Let's do negative 3. F of negative 3, that'll be negative 3 to the power of 4. Minus 2 times negative 3 to the third power. Minus 4 times negative 3 squared. Plus 26 times negative 3 minus 21. Well, negative 3 to the fourth power is still 81. Negative 3 to the third is negative 27 times negative 2 is a positive 54. Negative 3 squared is 9 times negative 4 is a negative 36. 26 times negative 3 is a negative 78, and then minus 21. 81 and 54 is 135. Minus 36 is 99. Minus 78 is 21. Minus 21 is 0. 3 is a root. Which means x minus 3 is a factor. Sorry, not 3, that's negative 3 is a root. So that means it's x plus 3 that's the factor. So what I'm going to do is I'm going to divide, I have two factors. So I have one positive and one negative root. I either have two more positive roots or those two roots are imaginary. Rather than testing out a bunch more numbers, I'm going to divide out the two roots I already have. The reason I'm doing that is this was x to the fourth here, fourth degree. If I divide out two roots, each time I divide out a root, it takes that power, that degree down by 1. If I divide out two roots, it's going to be x squared. And that we can either factor or use the quadratic formula on. So rather than exhausting the rest of these that we haven't tested yet, 7 and 21 are big numbers anyway. I don't really want to take those to the fourth power. Let's simplify our expression. So we have, I'm going to scroll down the screen here. X to the fourth minus 2x to the third minus 4x squared plus 26x minus 21. And I have factors of x minus 1 and x plus 3 that I'm going to divide out. So I'm going to use my synthetic division. I'm going to put 1 here, and my coefficients, positive 1, negative 2, negative 4, positive 26, and a negative 21. The 1 comes from the x minus 1. Remember this x minus c? We put c over here. So I'm going to drop this first number down, the 1. 1 times 1 is 1. Then we add. Negative 2 times 1 is negative 1. 1 times negative 1 is negative 5, or negative 1, sorry. We add there, negative 4 plus negative 1 is negative 5. 1 times negative 5 is negative 5. We add there, 26 plus negative 5 is 21. 1 times 21 is 21. We add there to get 0. What this means, of course, the 0 means there's no remainder. That's good, because it's a factor. There better not be a remainder. The 21 is our constant term. It's positive. The negative 5, x, is our x term. Negative 1, that's negative x squared. And the positive 1, that's x to the third. So after we've divided out the x minus 1, that's what's left over. So now let's divide the x plus 3. We divide x plus 3. Of course, we think of that as dividing by x minus a negative 3, because it has to be in that form of x minus something. So what we're really dividing by, or what we're going to use in our synthetic division, is the negative 3, excuse me. We bring down these coefficients. That's a positive 1, negative 1, negative 5, and a positive 21. So now we're going to do our synthetic division. We just bring down the first digit, the 1. 1 times the negative 3 makes negative 3 here. We add those. Negative 1 plus negative 3 is a negative 4. Negative 4 times negative 3 is a positive 12. Negative 5 plus positive 12 is positive 7. 7 times negative 3 is a negative 21. 21 plus negative 21 is 0. So again, that 0 tells us no remainder, which we better have no remainder because that's supposed to be a factor. What's left over here, the 7 is the constant digit, that's or constant term, that's positive. Negative 4 is actually negative 4x, and then the 1 is x squared. So this is what we have left after we've divided out those two factors. So what we're saying here is our original function, f of x, which was x to the fourth minus 2x to the third minus 4x squared plus 26x minus 21. We have factored it so far to x minus 1 and x plus 3. You gotta make sure I got the right one, 0. To x minus 1 times x plus 3 times this piece that's left over, x squared minus 4x plus 7. To find my remaining roots, I just have to factor this x squared minus 4x plus 7. Now I can try to factor it. It's not going to work if I try to use the reverse multiplication. So we're going to go to our quadratic formula. Where A is 1, B is negative 4, and C is 7. Remember our quadratic formula is negative b or opposite b plus or minus square root of b squared minus 4ac all over 2a. It's been a couple weeks since we looked at that. So b is negative 4, so opposite b is positive 4. Plus or minus the square root of b squared, so that's negative 4 squared, minus 4 times a is 1 and c is 7, over 2 times a, so 2 times 1. Inside the square root, again, I'm going to cheat a little bit on my order of operations. I'm going to combine a couple things. Negative 4 squared, first of all, is 16. 4 times 1 times 7 is 28. On bottom, 2 times 1 is just 2. (16 minus 28) is a negative 12, or 2. Let's look at simplifying that radical expression there. To simplify that, we need to simplify the square root of negative 12. And what I'm going to do is I'm going to split that into the square root of negative 1 times 4 times 3. Why did I do that? Well, because the square root of negative 1 is I. The square root of 4 is 2. I'll be left with the square root of 3. Can't do anything with that. So I'm going to put that back in here for the square root of negative 12. So I have 4 plus or minus 2 times I times the square root of 3 over 2. Now all that's left is to divide out by this 2. 4 divided by 2 is 2, plus or minus. That 2 just cancels out. So 2 plus or minus I times the square root of 3. So that gives us 2 roots. 2 plus I times the square root of 3 and 2 minus I times the square root of 3. So we have our roots. Our roots are going to be at 1, negative 3, 2 plus I times the square root of 3, and 2 minus I times the square root of 3. Remember, by the way, that these complex roots always come in pairs. There will always be 2 of them. I'm going to have you try another one here. I want to construct a polynomial function with roots 2 and let's go 3 minus I. So I'm going to give you a couple minutes to think about it, then we'll take a look at it. Remember, this implies a second root, which is going to be its complex conjugate. So there's 3 roots there that you're going to work with. Probably haven't had quite enough time to do all this yet, but let's just take a look and see if you're heading in the right direction. So the factors from a root of 2, 3 minus I, and of course the complex conjugate of 3 plus I. The factors we get, of course, are x minus that root. So the root of 2 would be give us a factor of x minus 2. A root of 3 minus I gives us a factor of x minus 3 minus I. And 3 plus I gives us a factor of x minus 3 plus I. So the first thing I'm going to do is distribute the negatives in those two roots. So this becomes x, the negative, think of it as a negative 1 times 3 is a negative 3. Negative 1 times negative I is a positive I. Here this will be x, think of it as a negative 1 again, times 3 is a negative 3 again. Negative 1 times I is a negative I. Those are our factors. Now I have to multiply them together, but what I'm going to do is I always take my complex factors and multiply those first. And I do, if there's more than 2 complex factors, if there's 4, I multiply the ones that are the conjugate pairs together, because those will simplify and get rid of the complex portions so that I don't have to work with the imaginary numbers for very far. So I'm going to ignore this for now and I'll come back to it. I'm going to multiply these two over here. So I'm going to have x times x, that's x squared, x times negative 3, scroll up just a touch here, that's negative 3x, and x times negative I, that's negative ix. I move on to my next term, the negative 3. Negative 3 times x, negative 3x. Negative 3 times negative 3 is a positive 9. I'm putting it off over there because that's going to be my constant. And negative 3 times negative I is a positive 3i. Notice I didn't put it under the ix because there's no x in it. Now I move on to the I. I times x is a positive ix. I put that under the negative ix. Those are going to cancel out. I times negative 3 is a negative 3i. I put that under the positive 3i because that's also going to cancel out. The tricky multiplication is right here, I times negative I. Well, I'm going to treat this as a 1i times a negative 1i. 1 times negative 1 is negative 1. I times I is also negative 1. So negative 1 times negative 1 is a positive 1. So I times negative I is a positive 1. So here I've got the x squared. Negative 3x and another negative 3x is a negative 6x. Negative ix and positive ix cancel out. Positive 3i and negative 3i cancel out. 9 plus 1 is a positive 10. Now I still have that factor of x minus 2 that I need to multiply by. So x times x squared is x to the third. X times negative 6x is negative 6x squared. X times 10 is 10x. Moving over to the negative 2, negative 2 times x squared is negative 2x squared. Negative 2 times negative 6x is a positive 12x. And negative 2 times 10 is a negative 20. So I've got x to the third. Scroll up a bit. Negative 6 and negative 2 makes negative 8x squared. 10 and 12 makes 22x, and then minus 20. So the polynomial function that had the roots of 2, x minus 3i, and x plus 3i, or sorry, the roots of 2 and 3 minus I, 3 plus I should say, that polynomial function is f of x equals x to the third minus 8x squared plus 22x minus 20. Any questions there? Okay. Any questions off the homework from Tuesday? Okay, good. So today our purpose is to wrap up Unit 1. Next week in Monday's class is Test 1. So for Test 1, I put this in the announcements, but for Test 1, you will have the full 2 hours to do the test. You may use your notes on the test. You may use your calculator if you have whatever you have, whether it's graphing calculator or regular calculator, you may use that on the test as well. It will be paper and pencil, so this will not be in my math lab. It will be a paper test in class. So let's wrap up Unit 1 here today. So we've been talking about polynomial functions. The next step from polynomial functions is rational functions. And rational functions are really a combination of polynomial functions. So let's say I have polynomial functions P of x and Q of x. A rational function will be of the form f of x equals P of x over Q of x. Now it could be as simple as f of x equals 7 over x minus 2. That's a rational function. It can be way more complicated. It can be f of x equals 3x over x squared minus 25. Or we could even have f of x equals 5x to the third minus 2x squared over x squared minus 5x plus 6. Those are all rational functions. So what we want to do is we want to look first of all at the graphing behavior of rational functions. So we're going to start out with simple rational functions and work from there. So probably our simplest rational function is that f of x equals 1 over x. So to graph this, we'll make a table and we'll make a graph. So values of x and y. If I put in negative 4 for x, y is negative 1/4. So negative 4, negative 1/4 is right there. If I put in -2 for x, y equals -1/2. Something like that. If I put in -1 for x, 1 divided by -1 is -1. So that's at -1, -1 right there. What happens if I put in 0 for x? I saw you mouth it there. It's undefined. You cannot divide by 0. If we do 1 divided by 0, it gives us an error. We can't do that. 0 is not in the domain of this function. Remember, we can never divide by 0. That's one of the ways we figure out what is excluded from the domain. So I need to figure out what happens in here, though, so I'm going to try a fraction here. Let's do a -1/2. If x is -1/2, y is actually -2. So we get an idea here of the graph. Looks something like this, hugging the axes as it goes off. Put in positive values for x. If x is 1, y is 1. If x is 2, y is 1/2. And we end up getting a symmetry here, actually called symmetrical about the origin. This is what's called an odd function. It's symmetrical about the origin. And we get a graph that looks like that. So that is our basic f of x equals 1 over x graph. Well, some things we can do with that graph. If you recall, if we added or subtracted to the x, it moves our graph along the x-axis. If we subtract, it moves us in the positive direction. If we added, it moves us in the negative direction. So what this is doing is taking what normally would have been the center. So we would have had our curve looking something like that. That would have been our center. And it's moving it over 3 units. So we're going to be centered around there now. So the graph is going to look something like that and this. So it just shifted it or translated it over 3 units to the right. If I do this, notice that's not attached to the x, that's to the whole function. Remember, that's actually the equivalent of doing -2 if we thought of the h of x as being a y instead of an h of x. We're actually subtracting 2 from the y when we do this +2 over here. So that means we're shifting on the y-axis. We're shifting up 2 units. So our center would be here now. And our graph looks like that. So just like any other function, the graph of f of x equals 1 over x can shift to the right or left or up or down by simply subtracting or adding to the x and then adding or subtracting outside of the x, basically to the y, to shift the graph. We could also do multipliers to it. If we did p of x equals 3 over x, all that's going to do is stretch our graph out. So we're going to go from being something like this to being stretched out vertically. So it's going to stretch this like that and like this. We could also multiply the x. If I did q of x, oops, I'm running out of room here. I'll write it over here. Q of x equals 1 over 5x. That actually shrinks our graph. Or actually, that's right. It dilates our graph on the x-axis. So 5x, now 1 behaves like 5. So it makes it tighter in like that. Like that. So all our common transformations, translations, and dilations apply to that. So we have a minute and a half left for our break. So I'm going to give you this to work on during our break. I want you to find the basic graph for me of f of x equals 1 over x squared. So make a table, put in values for x and y, and come up with that graph. So we're going to pause the video here so we got a minute left here and you can work throughout break. We'll go over this problem at 10:30. So let's just put in something like -4 again for x. Well, 1 over -4 squared is 1/16. So -4, 1/16 is a dot right there. I put in -2, -2 squared is 4. So 1 over -2 squared is 1/4. I put in -1, -1 squared is 1. So 1 over -1 squared is 1. If I can keep going with that, -1/2, -1/2 squared is a positive 1/4. 1 over 1/4 is 4. I get a similar curve, a little bit tighter to the axes, going like that. I put in positive 1/2. Well, positive 1/2 squared is 1/4. 1 over 1/4 is 4. So positive 1/2, positive 4. Positive 1. 1 over 1 squared is 1. And I can keep going. Positive 2. 1 over 2 squared is 1/4. And I see I get the mirror image of that curve like that. So that is 1 over x squared. Remember that if f of x was 1 over x, it looked like this. Doesn't quite lie on top of the green line there because it's not quite as tight of a curve, but you get the picture. And of course, just like the 1 over x, we can move that 1 over x squared graph around. But I don't feel any need to do that here. The symmetry, though, for each, 1 over x we said was symmetrical about the origin. 1 over x squared, we see the green curve is symmetrical about the y-axis. So what that's saying, symmetrical about the y-axis, if you recall, is an even function. Symmetrical about the origin is an odd function. So we see here that there's spots that these graphs don't cross. They're called asymptotes. Those asymptotes, so there's only one S in there. There Be careful. Those asymptotes are lines that the graph can't cross. Both of these functions have two asymptotes, and they're the same one. One asymptote is the x-axis. That graph cannot cross the x-axis. No matter what we put in there for x, 1 divided by x is never going to equal 0. The other is the y-axis here. We can never put x equals 0 in there because we can't divide by 0. Now the x-axis and y-axis are common asymptotes, but they're not the only ones. So let's take a look at these rational functions and talk about finding vertical and horizontal asymptotes. We're going to start out with vertical asymptotes. So vertical asymptotes are values that x cannot take on. In other words, they're values that are not in the domain of that function. However, not all values that aren't in the domain make asymptotes. So let's take a peek here. I'm going to look at the function f of x equals 2 over 3x minus 9. We cannot divide by 0. Because we cannot divide by 0, this denominator cannot equal 0. 3x minus 9 cannot equal 0. So let's solve it to see what values would make it equal 0. So 3x minus 9 equals 0. If we solve that, I'm just going to go through this really quickly. We would add 9, 3x equals 9, and then we would divide by 3. Gives us x equals 3. So what that means is x cannot equal 3. 3 is not in the domain of this function. So if I graph this function here, there is going to be a vertical asymptote here. The line x equals 3 is going to be an asymptote. But we said that not all of those values that are excluded from the domain are asymptotes. Well, what do we mean? When would they not be an asymptote, and how would we know? Well, if I have a function like f of x equals x minus 2 over x squared minus 4. Here, there are going to be two values that make that denominator equal 0. Two values that are not in the domain of that function. So if we solve for x squared minus 4 equals 0 to find out what those values are, I can add 4 to both sides, get x squared equals 4, and then square root. I get x equals positive 2 or negative 2. Those are the two values that are not in the domain of this function. However, if I look closer at the function itself, I notice that x squared minus 4 can be factored into x plus 2, x minus 2. I also see that I've got an x minus 2 in the numerator and an x minus 2 in the denominator. Those could be canceled out. So since that one can be canceled out, it is still not in the domain of this function. If I wanted to list the domain of this function, I still have to include both of them. So my domain here still goes from negative infinity to -2, combined with -2 to +2, combined with 2 to positive infinity. Still not in the domain, even though that factor cancels out. What it's saying is this one here produces, that's where the x plus 2 equals 0 gives us x equals -2. That is an asymptote. So if I'm graphing this, this graph cannot cross x equals -2. So as it approaches that line from either side, it's either going to shoot off to positive infinity or down to negative infinity. At x equals +2 here, there's no asymptote, but there's a hole in the graph. If I make a table here for values of x to find y, if I put in x equals 0, let's see, -2 over -4 is a positive 1/2. So 0, 1/2 is somewhere in there. If I put in x equals 1, set it on the table there for me. Thanks. I put in x equals 1. Well, 1 minus 2 is a -1. 1 minus 4 is a -4, so I get 1/4 there. If I put in 2, well, that's where I got 0 in that denominator. Can't do that. So let's put in 3, see what happens. Well, 3 minus 2 is 1. 3 squared is 9, minus 4 is 5. I get 1/5. So at 3 over here, I get 1/5. So what happens is that is going to give us a curve. It looks something like this, but at x equals 2, there is a hole in the graph, like that. So it doesn't produce an asymptote, but it still has to be excluded from the domain. So it gets excluded as a hole in our graph. So I want you guys to check on this function here. F of x equals 5x squared minus, I'll be nice, I won't put the x squared in there. We'll do 5x minus 15 over x squared minus 10x plus 21. I want you to find, first of all, the domain of the function. Second, I want you to find the equation of any asymptotes. Then I want you to find any holes that would be in that graph. So again, let's take a look and see how you've done on this so far. The key again is factoring. So we factor the numerator. 5x minus 15 is just 5 times x minus 3. And then factor the denominator, that x squared minus 10x plus 21 becomes x minus 3 times x minus 7. So our domain has to include or exclude x equals 3 and x equals 7. That's found by solving those two factors each for 0. So our domain goes from negative infinity to 3, unioned with 3 to 7, unioned with 7 to positive infinity. Asymptotes. Well, we notice that the x minus 3 could cancel out or cancels out. So we get a vertical asymptote at x equals a positive 7. That's an asymptote. Since the x equals 3 canceled out, we get a hole at the domain value of x equals 3. So whatever that curve is looking like, when it hits 3, there's just going to be a hole in the curve. So that's vertical asymptotes. The main thing to deal with the vertical asymptotes is making sure we don't divide by 0. We're looking strictly at the denominator, using the numerator only to see if we can cancel out any factors. Horizontal asymptotes are a little bit more complex. So if our function f of x is of the form, and we'll do this, a times x to the n plus blah, 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 over b times x to the m plus blah, blah, blah. Those are, remember, each are polynomial functions. Horizontal asymptotes meet certain conditions. So first we look at the degree of the numerator and the degree of the denominator. N is the degree of the numerator. That's the largest power on x in the numerator. M, of course, is the degree of the denominator. That's the largest power on x in the denominator. If m is bigger than n, which is almost always the case, then y equals 0, or the x-axis, is a horizontal asymptote. If the two have the same degree, this is why I didn't put the x squared in the numerator on that last example. If the two have the same degree, then y equals a over b is a horizontal asymptote. And finally, if m is smaller than n, there are no horizontal asymptotes. So let's take a look at some examples here. F of x equals 7x to the fourth over x to the third minus 2x squared plus 7x minus 9. What do we know about the horizontal asymptotes? We have a degree of 4 and a degree of 3. 3 is less than 4, so there are no horizontal asymptotes in that function. If g of x equals 2x minus 7 over x squared minus 9x plus 2, we have a degree of 1 in the numerator and 2 in the denominator. Remember, it's always the denominator first. 2 is greater than 1, so y equals 0, or the x-axis, is a horizontal asymptote. H of x equals 4x squared minus 3x plus 2 over 2x squared plus 9x minus 1. Here, we have a degree in the numerator of 2, a degree in the denominator of 2. Since 2 equals 2, we have to go look back at our A and B values. A is 4 and B is 2. So our asymptote is y equals 4 over 2, or y equals 2. So if I want to graph one of these polynomial functions, there are steps I'm going to take. Step 1, determine the symmetry. Remember, we can determine symmetry, symmetrical about the y-axis, if f of negative x equals f of x. It's symmetrical about the origin if negative f of x. Sorry, I should say f of negative x equals negative f of x. So all the signs in the function get changed. Next, find any y-intercepts. Y-intercepts, remember, are found at x equals 0. So you're basically just finding f of 0, find the y-intercept. Should only be one y-intercept, by the way. If there's more than one, it's not a function. Third step, find any asymptotes. Using what we just did, both vertical and horizontal. Roots are way more difficult to find on a rational function than they are in the polynomial functions. On the polynomial function, you would want to find the roots. Rational function, many times, that x-axis is an asymptote, so there are no roots. So at this point, you plot some points in each section. Bless you. What do I mean by in each section? Well, I mean by between the vertical asymptotes. Because the asymptotes will divide the graph into definite sections. So you need to figure out next to the asymptote, on each side, does it go down to negative infinity? Does it come in from positive infinity? What does it do near the asymptote and then between the asymptotes? And then, of course, just sketching the graph. So let's do an example here quick. Of f of x equals 8x squared over 2x squared minus 18. So if we're going to graph this, we want to determine symmetry. If there is any. So f of negative x, that's going to be 8 times negative x squared over 2 times negative x squared minus 18. Well, negative x squared is just x squared. So f of negative x is equal, to f of x. This is an even function, and it is symmetrical about the y-axis. The reason that's important to know is because as we graph, anytime we plot a point on one side of the y-axis, there's going to be an equivalent point on the same location reflected around the y-axis. Step 2. We want to find the y-intercepts. So we're going to find f of 0. Well, 8 times 0 squared over 2 times 0 squared minus 18. That's 0 over negative 18, which is 0. So the y-intercept here, there is a point. X is 0, y is 0. It goes to the origin. Step 3, we are going to find our asymptotes. So let's find our vertical ones first. There we go. Come on. Vertical asymptotes are where the denominator equals 0. So we're going to solve that 2x minus 18 equals 0. We're going to add 18. 2x squared equals 18. Divide by 2 to get x squared equals 9. And we'll square root. So either x equals 3 or x equals negative 3. Now we have to check to make sure neither of those factors gets canceled out. Well, on top, that 8x squared really doesn't factor into anything that will cancel out. This factors into 2 times x minus 3, x plus 3. On top, that's just 8 times x. Nothing's going to cancel. So there's no holes, there's only vertical asymptotes. Horizontal asymptotes. Well, if we look at this, the numerator, 8x squared, has a degree of 2. The denominator, 2x squared minus 18, has a degree of 2. There is no horizontal asymptote. So let's take a sketch of the graph here. We have vertical asymptotes at x equals 3 and x equals negative 3. So negative 3 right there, positive 3 right there. Pretend that goes through positive 3. Y-intercept at 0, 0. Now we just plot some other points. So f of x equals 8x squared over 2x squared minus 18. Let's see what happens in the middle here. So we got x equals 0. Let's see what happens at x equals 2. Well, y is going to be 2 squared is 4 times 8 is 32 over 2 squared is 4 times 2 is 8. Well, minus 18 is negative 10. So that's a negative 3.2. So at 2, negative 3.2 is a point like that. Positive 2. Oops, that was positive 2, sorry. Next I want to do negative 2. Negative 2. Well, negative 2 squared is just still 4, so it's still going to be 32 over negative 10, which is negative 3.2. So this is showing us, if we plotted more points, is we're going to get basically a parabola in here, similar to a parabola, but it's restricted at those locations. Let's see what's going on outside at negative 4. Well, negative 4 squared is 16 times 8 is 128. 16 times 2 is 32 minus 18 is 14. That is, let's see, 128 divided by 14 is 9.142857 approximately. So that is negative 4 and 9 up here. Positive 4 is going to give us the same thing. I'm going to start using the fact that we know it's symmetrical about the y-axis here. Let's try a positive 5. 5 squared is 25 times 8 is 200. 25 times 2 is 50. Minus 18 is 32. So that is 6 point something. So at negative 5, we're going to have the same y value. Let's go at 10. Let's get this over with. 10 squared is 100 times 8 is 800. 100 times 2 is 200 minus 18 is 182. That's going to be 4 point. How is that 5 point? 800 divided by 182 is 4.4. So out here at 10, we're down at 4. So we're getting this curve going something like that. Same over here. Now you might be thinking this process of graphing rational function is not very precise. It isn't. It gives us some critical points of it, that y-intercept, and it gives us the asymptotes. That's really all we're looking for. We're not looking for precise graphs. But it is a tedious process. Okay, so that is basically all of our stuff for rational functions. There is, by the way, I should throw in here, we can occasionally run into something called a slant asymptote, where the asymptote is at a slant. If the degree of the numerator is equal to 1 plus the degree of the denominator, it doesn't guarantee it, but there could be a slant asymptote. So what that is that is an asymptote on our graph that goes at an angle. And the graph approaches that line. You can get graphs that look something like that and that, at that slant asymptote. Well, how do we find it? Well, remember, if f of x is of that form, p of x over q of x, if you divide these out, p of x divided by q of x, you will get the equation of the slant asymptote. It's going to be a linear equation. So y equals whatever that equation is going to be the linear equation for that slant asymptote. Any remainder has to be dropped. You can still have a remainder, you're just going to ignore it. We got time, I can do a quick example here. So let's say f of x equals 3, let's do 3x. Yeah, let's just do this. 3x squared minus 7x plus 2 over x minus 5. I'm going to divide that out. Now, since I have x minus 5, I could have used synthetic division here, but I just want to review the long division here, just in case. Because if that's not a 1 in front of the x, you're not going to be able to use synthetic division. So 3x squared divided by x is 3x. Multiply it back through. 3x times x is 3x squared. 3x times negative 5 is a negative 15x. We subtract. 3x squared cancels out. Negative 7 minus 15 is a positive 8x. Bring down the 2. 8x divided by x is a positive 8. 8 times x is 8x. 8 times negative 5 is a negative 40. So again, the 8x cancels out. 2 minus a negative 40 is 42. We're going to ignore that remainder. So we have a slant asymptote here at 3x, y equals 3x plus 8. So you guys remember how to graph linear equations. So starting at 8, going up 3 over 1. That's going to be an asymptote. I didn't draw that real well. That's going to be an asymptote for that rational function. Okay, so there is homework from last time that is due. I believe that would be 4B that is due tomorrow. Tomorrow's Thursday. Quiz 4 is going to be due this Friday. Then, of course, on the material from the day, homework 5A will be due next Tuesday. But of course, the big thing coming up, exam 1, is in class on Monday. If there are questions on this homework 5A, I will answer those for you at the beginning of class. But you will have the whole class time to take the test as well. If you need additional time, we can arrange that. I don't want anybody to go over 3 hours, but we can give you up to 3 hours if you need to. So we have a couple minutes here. Let's just kind of quickly review some of the topics that are going to be on this test. You know, everything we've covered so far is going to be on this test, but we're going to have equations and inequalities. We can have equations with absolute values. Or inequalities with absolute values. We can have rational equations and rational inequalities. So there's a rational equation we could solve. There's going to be quadratic equations and equations in quadratic form. You might have x to the 8th minus 3 x to the 4th plus 2 equals 0. Have to solve that. It's in quadratic form because this power is twice that power. There's going to be graphing, of course, of all sorts of equations. Graphing, there will be linear, quadratic, of course that's parabola, polynomial, and rational, as we just saw, along with also absolute value. You also might be asked to graph piecewise functions. You'll be asked to work with complex numbers, perform operations on them, realize a denominator. Using complex conjugates. You'll also be asked to work with radical numbers. Doing all the things listed above up here, doing operations with them, rationalizing denominators and using the conjugates, but then also simplifying. That's like taking the square root of 20 and separating it into 2 times the square root of 5. And of course, there's things like formulas. Midpoint, slope, and distance formulas. And that's pretty much it. All of our stuff with functions and polynomials is also fair game. Or, sorry, functions, as far as evaluating functions, composites, inverses, and so on. And then, of course, we have our polynomial functions, roots, and stuff like that that we went over at the beginning of class. It's a big bite to take. We do slow down just a touch after this first exam, but we'll still be flying through material at a pretty fast pace. Anybody have any questions on any of these topics here before we end it for the day? Okay, so we have a lot to do here before Monday. You have homework assignments to finish up and to start, quiz to do, and exam 1. You'll notice in my math lab, there is an exam 1 review. If you complete that review, every type of question that's on the exam is in that review at some point. Not every question in the review will be on the exam, but every type of question that would be on the exam is in the review. That is worth up to, if you complete that, 20 points extra credit. I prefer that you have it done before you take the test if you're going to use it for studying, but I won't grade it until next Wednesday. So after class next Wednesday, I will go through and I'll see who has completed that, and that'll go in as their 20 points. Any questions? Okay, well, you guys have a great day, great weekend, and we'll see you on Monday.